guys. Hello, thanks very much for having me. It's great to be able to chat to people who are interested in astronomy. It's a nice change from just any kind of random group of people that you might chat to about what you're doing. So I suppose I'm going to talk to you guys today about gamma ray bursts and type 1 CBL supernovae. So I suppose you've probably heard about supernovae before, but have many of you heard of gamma ray bursts before? Yeah, great. Okay, so as was mentioned earlier by Mick, I recently defended my PhD thesis back in mid-January about the connection between gamma ray bursts and these types of special supernovae. And I'm also involved in the AirSat-1 project. So as part of my PhD, I was also involved in testing, building AirSat, making sure that it was going to survive in space, and then later on operating it as well. So I've kind of seen the middle of the project towards the end of the project now. I'm going to try and give you an overview of sort of my PhD work rather than the work on AirSat today. But I'm happy to take questions about AirSat as well if people have them. Okay, so first thing we have to do is supernovae and gamma ray bursts are both ways that massive stars can die. So they're the end stage of massive stars. So you have to review that first. Okay, so a gamma ray burst is normally detected as this kind of very rapid pulse of gamma rays. So this is a detection that AirSat-1 made. It was back in November, 30th of November. So you can see there's kind of this background level of gamma rays, and then there's a big spike. And then these gamma ray bursts tend to have what we call a Fred profile. So it's fast rise and exponential decay. And then it kind of returns to the background rate. On the right-hand side, there's a picture from the Fermi Space Telescope, and that is showing a gamma ray burst basically outshining the Milky Way in gamma rays. So these events are putting out lots and lots and lots of light. So they're comparable to all of the stars in a galaxy, so hundreds of billions potentially. So like it says there, it's 10 times the sun's energy output in its whole lifetime in, 1 second to 1,000 seconds, depending on the gamma ray burst. So that's really, really cool, because these are very extreme physical conditions. You can't necessarily study these in a lab on Earth. You have to look for them in space. Okay, so the reason we have to go to space is we're all sitting here on the Earth, protected by the atmosphere and Earth's magnetic field. So gamma rays are not reaching the surface of the Earth, nor are any charged particles that might come from these events either. So on the left-hand side is the Fermi Space Telescope. Fermi has a couple of different ways of detecting gamma rays. So on the top here is the Large Area Telescope, or the LAT. And these kind of cylinders that you can see here are also for gamma ray burst detection. And then in the middle, there's something called SFOM. So have people heard of SFOM? It's a relatively recent telescope that the Chinese and the French developed. And that's also looking for gamma rays at the moment. Then on the right-hand side, you have AirSat-1. So AirSat-1 is a really small satellite. Like these ones take up, the size of a whole room. But there's some of the AirSat-1 operators' hands there for scale. So AirSat's really miniaturized. So it's got a very small collecting area, but it is still able to detect gamma ray bursts with that small collecting area. So Fermi was designed in the early 2000s. It's probably early 90s technology or early 80s technology. But AirSat is, more modern technology that's been really miniaturized and put into a tiny package that fits into a CubeSat. Okay, historically, we thought there were two different types of gamma ray bursts. So we thought there were these short gamma ray bursts that lasted for less than 2 seconds, and then there were long gamma ray bursts which lasted for more than 2 seconds. But around the time I started my PhD, we started finding kind of holes in this definition scheme that we had for about 30 years. So basically, we have moved from our long and short definition into a definition based on kind of the physics that's happening in these events. So we have what we call merger gamma ray bursts, and merger gamma ray bursts feature multiple neutron stars, so normally two neutron stars or a neutron star and a black hole, that collide with each other and merge, and then they release radiation in the form of gamma rays that we see as a gamma ray burst. Or we have collapsars, which is the one that I'm most interested in. These are typically long bursts, but they're not always. So we have recently found what we call a short collapsar. So it's a burst that, you know, is less than 2 seconds, but based on its optical light curve and its radio light curve, we think that it is associated with the collapse of a massive star. So collapsars associated with massive stars, mergers associated with neutron stars. So that's the basic paradigm that we have now. We've moved away from the duration-based classification. So when neutron stars merge, or when a massive star comes to the end of its life, it forms a black hole, or potentially a magnetar. So that's a magnetized neutron star that's spinning very rapidly. And this is called the central engine of a gamma ray burst. And the central engine launches this thing called a jet. And this jet, excuse me, this jet escapes from the star, basically. So it tunnels out through the star's layers, pushing material ahead of it as it goes, breaks out into space, and then eventually it runs into the material that is surrounding the star. So the interstellar medium, or perhaps material that was thrown off by the star during its lifetime. And as that jet slows down, we get two different types of radiation. So when material inside the jet collides with other material within the jet, we get these things called internal shocks. And internal shocks are what generates the gamma ray burst. So that's the gamma ray burst itself is coming from inside the jet, whereas if I'm here on Earth and I'm looking for this gamma ray burst after that time, so after the first few seconds, I'm typically seeing what's called the afterglow. And the afterglow comes from the external shocks. And external shocks are located here. And the external shocks are basically, the jet has lots of kinetic energy, and the kinetic energy is being converted into light. So as it runs into the surrounding medium, it slows down, and that is released as photons. So the gamma rays are created in the jet, afterglow is created just outside the jet. And the afterglow goes from X-rays, very, very high X-rays, potentially, you know, bordering on gamma rays, all the way down to radio. So it's a synchrotron spectrum. So it's created by electrons gyrating in magnetic fields and giving off light that way. Okay, so an interesting thing about the jet is that due to the rapid motion of the particles within the jet, so mostly electrons and positrons, those are moving very, very rapidly. It's an ultra-relativistic jet, and it's moving pretty much at the speed of light. It's very, very, very close to the speed of light. So that means that the radiation, because of relativistic effects, is preferentially emitted along the axis of the jet. Okay? So you're not going to necessarily see radiation at a large angle from the jet. And this gives rise to something that we call orphan afterglows. So I mentioned that we have this initial pulse of gamma rays, and we call that the prompt emission. The prompt emission isn't visible to an observer who observes outside of the jet. If I'm observing within the jet, I'm along this line, along the jet axis. However, if I'm an off-axis observer, I'm outside of the jet. Okay? If I'm outside of the jet, I won't see the gamma ray burst. Okay? That radiation is only going out along the jet. It's not coming out, you know, kind of perpendicular to the jet. So I can't see that. However, when the jet slows down, the cone that radiation is emitted into gets wider. And over time, that means that I get to see the afterglow. But the prompt emission is gone by that time, so I can't see it. Okay? So this graph on the right-hand side is basically showing that depending on the angle that I look at a gamma ray burst from, I see a very different event. So if I was observing pretty much within the jet, so if I was here somewhere, say, I would see this blue curve, whereas if I was out here somewhere, I might see something more like the green curve. So I'm getting less and less flux from my gamma ray burst the further away from the jet I go. Okay? Another interesting thing is not all jets are created equal. So the velocity of material within this jet, there's a few different kind of shapes that it could take that we could think of. So one shape could be, okay, along every angle that's within the jet, the same amount of energy is being directed. Okay, so it's just an even profile across the jet. Any angle has the same light emitted from it. However, we could also think of more complicated ones. So we could think of something where in here, along the very edge of the jet, there's less energy, and perhaps towards the center, the energy is greater. Okay, and that would be something that we would call a Gaussian jet. So it has like a Gaussian profile in energy. The reason that I'm interested in this is we don't know when we see a gamma ray burst initially what angle we're observing the jet from. If we see the prompt emission, then it's very likely that we're within the jet because, like I mentioned, we wouldn't see prompt emission at all if we weren't within the jet. However, if we go slightly off what's called off axis, so outside of the jet, we could see very different results depending on the structure of the jet. And it's interesting to be able to infer what the jet is like just based on your viewing angle. So the viewing angle is a parameter that we can determine through our observations. But then by looking at this afterglow that's shown in the right-hand plot, we can basically say, okay, it's either a Gaussian jet or a top hat jet or something else. So basically different types of jet produce different light curves, and this makes it harder to check for the presence of the gamma ray burst. All right, so that was gamma ray bursts. Does anyone have any questions on gamma ray bursts at the moment?
Is the jet caused by the rotation, either of the merging of the neutron stars or the spin of the star that collapses, so it's at right angles to the spin axis?
Yeah, so it comes out along the polar axis, so the spin axis basically. And the reason for it is it's something to do with the Blanford-Znajek process, so the BZ process. And the BZ process basically, there are it's a black hole at the center of these events, we think, in a lot of cases. That black hole has a magnetic field, and the magnetic field is going both through kind of normal space, and it's also going through the black hole as well. And there are special effects within a black hole that can give rise to energy being released along the polar axis with that effect, basically.
What kind of frequency are we looking at in the gamma rays?
Frequency, so optical light is 10 to the 14 hertz. So I suppose it would be 10 to the 20 or 10 to the 22, something like that.
Mm-hmm.
Yeah, greater than optical anyway. I know what it is in EV. It's 1 MeV basically is a typical gamma ray energy. Yeah, so 1 MeV, well, typically, like, one of the problems is no one agrees on where the line between X-rays and gamma rays is, but 1 MeV is a good definition because a 1 MeV photon is able to pair produce electrons. That's kind of one way you can think of it. It has double the energy that is required for creating an electron, so it's able to create electrons on its own if it decays.
Could I ask, this notion that what you see depends maybe on the angle you were to it?
Yeah.
Has this helped in tracing back source of where it's coming from?
So I suppose you kind of already know where it comes from because you see a point of light in a particular part of the sky. You don't know necessarily at the beginning whether you're on axis or off axis, but if you monitor it over time, you can definitely, like, it's more that we would infer what direction the jet is going in rather than...
There's never a doubt what the source of the gamma ray is when you get them.
There could be if it was, for example, gravitationally lensed. If there were multiple, if there was a big cluster of galaxies in the way, you could see multiple gamma ray bursts all at once. I think that's only happened once though, so it's quite unlikely. But yeah, like gamma ray bursts can be seen like out to redshift 8, so like 12 billion years ago or whatever that is. It's a long time. They've been around since there were stars, basically. Yeah.
The collision between two neutron stars that are given out is the neutron stars are spinning.
They are, yeah.
They're not spinning in the same direction.
Not necessarily, no.
So when they collide, how do you know which way the jets are going?
Well, I suppose you would get a new neutron star that has its spin axis aligned with, I guess, the average of those two systems.
Oh, okay.
I mean, it's certainly more complicated than just the average, but that, as a first approximation, it could be, that you would have the average of those two systems.
So when two neutrons, you end up with one neutron star.
Yes, in
same
theory.
Black hole.
Yeah. Now, it's not exactly just one neutron star. If I go back to this one, this light that's being emitted here,
The blue one, the light blue.
in any of them really,
Okay.
basically these deviations from these dotted lines. So the dotted lines are if you just had a kind of a normal gamma ray burst, but these are called kilonovae, and kilonovae are formed in basically clouds of neutrons that are capturing lots and lots of they're basically forming new elements, and those new elements emit radiation when they form. So you're getting that light emitted there. But this is a very rapid process that happens on the time scale of like hours to days. So it's hard to find these.
And when you say new elements, what are you talking about there?
So when neutron stars collide, there's loads and loads of neutrons around, and there's lots of electrons around as well. So you can start forming new atoms basically. Starting at hydrogen basically and going all the way up as far as you like basically.
Yeah, they're not new elements.
No, as in like the elements we know,
Oh,
but
yeah.
we start in basically a soup of neutrons, and then those neutrons capture each other until you end up with more and more elements or heavier elements. And that is one of the sources of like most of the heavy elements in the universe. Stars can't produce anything greater than iron, so there has to be some other method, and one of the methods is neutron stars and merging, and the other method is supernovae.
Thank you.
All right, I'm going to go on if that's okay, guys. Okay, so core collapse supernovae. So we talked about gamma ray bursts. That's one way that a star can die. We also have core collapse supernovae. So over time, stars are kind of kept alive by hydrogen fusing into helium. That releases energy, and that energy resists the gravitational collapse that would normally turn the star into a black hole eventually if it kept going. So over time, hydrogen fuses into helium, then it fuses into beryllium, then it goes to carbon, nitrogen, oxygen, gets up to silicon and a few others. Eventually it reaches iron. And the thing about iron is that when you fuse two iron nuclei, it doesn't release any energy. So it takes in more energy to fuse them than it releases. And so you no longer have this source of heat in the center to keep the star alive. And so the star starts to collapse. And as it falls inward, the central layers get compressed. What happens there is that the elements that you had, so you had some electrons and you also had some, iron, silicon, oxygen, they're being compressed. And so it's a really weird process that happens. But basically, everything turns into neutrons. So protons in those nuclei get crushed so much that eventually the nuclei just break up. So then you have free protons from those nuclei. You also have neutrons and you have some electrons. The electrons get basically forced together with the protons and turn into a neutron. When this happens, it releases loads and loads and loads of neutrinos. And those neutrinos essentially are what blow the star apart. So the force of neutrinos normally don't interact with anything, but if you make it dense enough, they do. And if there's lots of them, they have enough energy to blow the star apart. So that's how a typical supernova happens. And this image on the right-hand side is of the Crab Nebula, which used to be a supernova and has now got a pulsar at the center, so a rotating neutron star. Okay, so how do we find them? So basically, every day I go and check my emails, and there are a huge list of new supernovae that have been discovered, and there are also a big list of supernovae that have been classified. So there's a difference between discovery and classification. Classification normally comes second after we've had a few more observations of a new transient. So we use something called the Zwicky Transient Facility, which is based in California, I want to say, has a huge field of view. So this huge box here is the field of view of the telescope that's used for this survey. So you can see the full moon is here, Andromeda is here. It's an enormous region of the sky that it's taking, a photo of. It gets a picture of the whole area of the sky that it's able to see. So basically all of the northern hemisphere sky every two nights. So it has two observations and two filters of each part of the sky every 2 nights. And basically what we do is we look at a picture from the night before or a couple of nights ago, and we go, okay, there was a galaxy here. Then we look at tonight's photo where there's this new bright spot in the image, and that bright spot is a supernova. You can tell from the fact that everything in the image is a lot darker in the second one, but the supernova is really, really, really bright. And the scaling is such that the galaxy looks quite dim by comparison. Okay, So yeah, basically we get a list of these transients reported to us in our emails, and then we kind of whittle it down a little bit. Like this thing generates about 10 million new alerts every night. So there's 10 million things in the sky that have seen. About 1 million of them are actually like interesting astronomical events. Some of them are planes, asteroids, that type of thing. And then you basically start whittling it down. And we're able to whittle it down to like 10 new supernova candidates every night, but that's still a lot. Like over a month, that's 300 things that you have to go and follow up, which we don't do because we don't have enough telescope time to do all of that. So a lot of them are slipping through the cracks is one of the issues we have, but I can talk about it a little bit later. Okay, so we've discovered a new transient. So we think it might be a supernova. If it's a supernova, what we would expect is a very rapidly rising light curve in optical light. So the light that we take pictures in. So typically they might rise up to 18th or 17th magnitude, possibly a bit lower as well. They rise on a time scale of around 10 to 15 days in their rest frame. It can be longer, obviously, if it's at redshift 1 or 2 or 3. They're hard to see past redshift 1. I was involved in a project during my PhD to go and study one that was at about redshift 1, and we needed James Webb to go and look at it. So it was...
And did you get James Webb?
We did, yeah. We got James Webb and Hubble to look at it, which is really, really cool. I can chat about that later. But yeah, so I mentioned that you've got these loads of neutrinos that are blowing the star apart. Those neutrinos also then run into the stuff that's inside the star while they're blowing it apart, and they cause the synthesis of radioactive nickel from basically the iron that was there originally. So you get radioactive nickel. Radioactive nickel decays, it emits gamma rays, but again we're still stuck inside this really dense cloud, so the gamma ray just bounces around for ages losing energy. It's a process that's called thermalization. So the gamma rays eventually turn into optical light. They lose so much energy in collisions that they turn into optical light, and that light diffuses out of that ball of gas on a time scale of about 15 days, and that's why that's a 15-day time to peak. And then they've hit their peak, so then they just gradually decline as the gas is expanding outwards. It's becoming transparent gradually. Light's escaping all the time, but eventually you run out of light, so you end up far down there on the bottom. There's another powering mechanism that takes over a bit later on. So you see where there's this kind of change in slope here. In the light curve, that's basically where radioactive nickel has kind of reached a few half-lives of radioactive nickel, so there's not very much of it left, and cobalt then takes over. So nickel turns into cobalt. The supply of cobalt is increasing while the supply of nickel is going down, so eventually cobalt becomes the dominant radiation that you're seeing. Eventually they all get to iron, which is why these things don't go on for ages and ages. Interesting thing about how we know it has to be nickel that was produced during the explosion is that the half-life of nickel that's radioactive is only 6 days. So if it's been in the star for hundreds of millions of years, it can't be the stuff that's powering the light curve. It doesn't live for long enough. Okay, so back to ball of gas expanding out into space. So I made this very scientific diagram from my PhD talk to explain how this works. So you're going to learn about supernovae, and you're also going to learn about spectroscopy a little bit here. So we've got this radioactive nickel inside. It is wrapped inside this thing called the photosphere. The photosphere, when you look at, say, the sun, it's the thing that we see as the surface of the sun. It's not actually the surface, but it's the position where light doesn't come directly out from the sun. So basically there's light inside that bouncing around. We can't draw a line to where it came from. It went on some random path before it came out. So that's your photosphere. Can't see inside this region. However, outside, there's all of this gas that was blown off during the explosion. We can see through that. So that's a low density gas that we are able to see through. So this is very, very hot because there's gamma rays inside it and they're trying to get out and they're heating up the gas. So we've got kind of this underlying black body spectrum, somewhat like the sun, You have a question?
No, just when you say it's very, very hot, is it hotter than the center of our sun?
Yes. Inside, yes. It'd be, well, in theory, it's 14 million degrees. In theory. You can't go measure it, but like, to get the fusion reactions to go on, it has to be quite hot. The outside of it is not that hot. The outside of it could be like say here, could be 16,000 degrees. So it is hotter than the sun's surface, but it's not hotter than the sun's interior, for example. Yeah.
What does the Y represent in the sphere along with the NI?
It's a gamma, not a Y.
Oh, gamma.
Yeah, it didn't come out very well, but
Right.
it was like the night before my thesis. So I didn't, or the night before my viva, so I didn't bother changing it. Yeah, so we got this radioactive nickel, produces the background spectrum. Then outside, we've got all these absorbing materials, right? So these absorbing materials kind of steal light from that nickel black body spectrum that we're getting. So basically what you end up with is this spectrum where you've got these big dips and you've kind of got a general kind of black body shape that you're kind of trying to fit to a little bit, but we're mainly interested in these dips and what we can learn from these dips. So those two dips are caused mainly by iron and by silicon. So it just so happens that those are the elements that have lots and lots and lots of lines, so it's easy to detect them basically, and they're abundant in the ejecta. The ejecta is this gas cloud around the supernova. Okay. Right, so once I get this email that tells me that there's been new transients discovered, I need to find out whether it's a supernova or not. So the first thing we do is we look at the explosion mechanism, which we can tell from the light curve or from the spectrum, but primarily from the spectrum. So a thermonuclear supernova is, you've heard of them, white dwarf, has a companion, takes gas from that companion, it eventually gets to a certain mass, and that causes it to implode, essentially. The more interesting ones are the core collapse supernovae, because a single star can form those, so there should be loads and loads of those. There's loads of single stars. They have to be quite massive, they have to be about 8 times the sun's mass or greater. The ones that I'm looking at probably started at like 40 to 60 solar masses, so they're huge. Like, they're incredibly big stars. Obviously very blue as a result. Like they're fusing a lot of hydrogen, and they get very hot temperatures in their stars.
So they're young.
They're young, exactly. They live fast and die young. So one other thing that they do is, because their radiation output is so high, they actually blow away their outer layers. So they blow off the kind of outer shells of helium and hydrogen. And that's one way that we can work out from the spectrum what type of supernova it is and what type of star formed it. So the first thing we look at is there hydrogen? If there is, it's a type 2 supernova. If there's no hydrogen, the next thing we do is look at helium. So hydrogen is the shell on the outside, helium is the shell that's just under that. So if you've removed hydrogen, there should be helium. If you've removed helium, then you have to be in further again. So if there's helium, it's a 1b supernova. If not, the last thing to check is, are there broad features in the spectrum? So we'll see an example of that in a minute, but basically then you're down to a 1C or 1CBL supernova. So I'm interested in 1CBL supernovas, so 1C broadline supernovae. And they look a little bit like this. So bottom one is a type 1C supernova. So this is one that doesn't have hydrogen and it doesn't have helium. However, it does have loads of other elements. So it's got calcium, iron, silicon, oxygen. But these are very narrow lines, okay? So they're very kind of well-defined features. The lines are created by basically the motion of the gas. So it's essentially that some of the lines, you've got a huge cloud of gas. Some of it is moving towards you, some of it's moving away from you. You get slight red shifts or blue shifts of the absorption line that you're looking at. And that is what creates the width of a line in a spectrum, for this purposes anyway. Temperature also affects it, but mostly it's going to be down to motion of the gas. Yeah. So you can see when you look at the 1CBL spectrum, those lines are a lot wider. So essentially, we think this is because 1CBL spectra have very high expansion velocities. We don't know why, but that's kind of what my research is about, so you'll kind of see what I think the reason is in a minute. So 30,000 kilometers per second, which is 10% of the speed of light. So somehow these events are getting several solar masses of stuff to 10% of the speed of light, that's an unimaginably large amount of energy to do that over a few days, for example. Yeah, but anyway, for the moment, just remember that they have very wide features, and that the main features are iron and silicon. Okay, so finally we're on to, what I've been studying. So it's called the gamma ray burst supernova connection. So back in 1998, we found a supernova at the same position and at the same time as a recent gamma ray burst. So there was a gamma ray burst, and then a day or two later, there was this kind of rising light curve that eventually peaked after 15 days. And when we got a spectrum of it, it's a 1 CBL supernova. So this is interesting, but not surprising. So we said they had to be massive stars. We know that they have to kind of remove their outer layers to be a 1 CBL, and we know they have to be rapidly rotating to be gamma ray burst generating stars, essentially. So, I know exactly where I was on the 25th of April 1998, because this is a really, really important day in GRB-SN science. So this is where I was. Now, we've had 60 of these GRB-SN events since then. Okay, so there's enough of them that you believe that it's a real signal. It wasn't just a chance coincidence that there was a supernova and a gamma ray burst in the same galaxy on the same day. Could happen, but it wasn't, because we've seen 60 more of them. In every case, it's a long gamma ray burst. Now, we've said we've moved away from that, so just think it's a collapsar gamma ray burst. So it's a star that collapsed, accompanied by a 1 CBL supernova. And we know that most of the nearby gamma ray bursts have a 1 CBL associated with them. But, and this is the really important bit, we've got loads and loads and loads of 1 CBL supernovae that don't have a gamma ray burst. So you might remember earlier I was talking about the fact that there's viewing angle effects here. Yeah. We can be observing a gamma ray burst in the jet, in which case you see the gamma ray burst, or if you're outside the jet, it becomes really hard to see the gamma ray burst. So this is basically emphasizing all of the green bars are 1 CBL supernova that we've observed. Okay, and this is going back to 1997. You can see that the rate of the orange and blue ones, which are 1 CBLs that had a gamma ray burst, is pretty constant, but suddenly we found loads more 1 CBL supernovae, and that's because of new telescopes, basically. We've got telescopes that can see wide areas of the sky, and that gives us, in optical light particularly, gamma ray burst kind of monitoring telescopes can naturally see, large areas of the sky because gamma rays pass through a lot of materials. But, an optical telescope has generally a narrow field of view, or, you're limited somewhat in the amount of the sky that you can see all at once. But we've got this new, Zwicky transient facility came online here, and you can see there's a massive increase after that. And there was a bit of an increase prior to that because we had another kind of Pathfinder project for that was increasing them.
Whereabouts is based in California?
Sorry?
Whereabouts this is in California?
Palomar.
Yeah.
Yeah. So there's been telescopes there for decades.
They put it down to the Palomar Schmidt.
Yeah, the
42-inch, 48-inch
yeah.
Ocean Schmidt.
Yeah. So it's a really cool machine because it can kind of taking a whole picture of the sky every 2 days is pretty cool. Yeah. So basically, we're finding loads of 1 CBL that don't have gamma ray bursts, and it's confusing because you would sort of expect that if they can produce, some of them can produce gamma ray bursts and others can't produce gamma ray bursts, so, or don't appear to.
That's
exactly.
You don't see them.
No, yeah. So it could be the viewing angle effect, or it could just be that they don't produce them. We don't know, and I wanted to figure out why. This is probably the nicest picture in the whole talk. But basically, this is what's called a Wolf-Rayet star. So our criteria were that it needs to be a massive star, so it needs to be 8 times or more the sun's mass. rapid rotation, and it needs to have no hydrogen or helium inside the star. So this is a James Webb observation of what's called a Wolf-Rayet star. Wolf-Rayet stars rotate very rapidly. They're surrounded by these clouds of glowing red gas, which is normally hydrogen or helium. And they're massive enough to form these collapse stars at the end of their life. So they're a really good candidate for 1CBL supernovae and for gamma ray bursts. The only problem is, although we can observe, we have directly observed Wolf-Rayet stars, we haven't observed one right before a supernova. And I think there's only like 2 or 3 stars where we've actually been observing them or like had historical images of them prior to a supernova of any kind. So it will happen in the next few years, I suspect, just because we've got better telescopes and we look back further in time. But it's hard to do. Like, they're common in the universe, but they're not common nearby necessarily. Not common enough to be able to like observe stars all the time in these events. Okay, so I might. How am I doing for time? Am I way over?
I still think it there.
No, you're good, Phil.
You good?
Yeah.
What time is it?
It's 6:15 now. Another 15 minutes.
Yeah. Okay.
Yeah.
Right. We'll have time for this then. Okay. So, what does a gamma ray burst supernova look like? So, I mentioned, we've got these declining light curves for gamma ray bursts. We've got these rise and peak and then fall off light curves for 1CBL supernovae. So basically, just add them together. That's essentially what you get. You get this part is the gamma ray burst, then you get a bump because of a supernova, and then you kind of return back to the gamma ray burst and decline over time. I mentioned about viewing angle effects. So some of these are probably because we just missed the gamma ray burst because we weren't within the jet. We couldn't see the gamma rays. How do I know this? Well, we have one example out of all 60 that we found where we had kind of a smoking gun signature that we were viewing a jet from a high viewing angle, so you were not able to see the gamma ray burst. So in 2020, so the year I started my PhD, there was this event called 2020 BBC, and this was a 1CBL supernova. So we found a 1CBL supernova where we had a declining light curve, but for once the declining light curve wasn't actually due to a gamma ray burst. There's other things that can cause that as well. It did its normal kind of peaking thing, but someone decided to look at it in X-rays. And we know there was no gamma rays, so we checked back through the archives from gamma ray telescopes. There wasn't any X-rays detected from that position at that time. However, what we do have is this point here in X-rays, so the black points are the X-rays. First is a non-detection, so the down arrow is basically saying the flux was below this in X-rays, but we don't know how far below. So there's nothing, and then on about day 3, we get something. So do you remember I showed that there was like this kind of peak, and then it turns over and goes back down, or an off-axis gamma ray burst? That's exactly what you'd expect if you were viewing a gamma ray burst at about 23 degrees outside of the jet. So we know it's possible. It's not just, science fiction. We definitely have an example of it here. But it is still really hard to find these, and this explains why there's only one. So these supernovae, they get up to magnitude 17 sometimes, but more often about magnitude 18. However, these are simulations of realistic gamma ray bursts at different viewing angles. Okay, so as we go, the colors basically indicate different viewing angles, and the different types of lines indicate different types of jets, but don't worry about that. What you have to take away is this is 22nd magnitude, so it would be quite difficult for our telescopes to get this. And you can see that a 15-degree observing angle, and you can't see the gamma ray burst actually go anymore. In optical, at least. So how did we see it? Well, we used X-rays. So this is a typical detection threshold for an X-ray telescope. You can see that even 20 degrees, perhaps even 30 degrees off axis is visible to an X-ray telescope. So that's what we have to do. So what my Collaborators and I did was when these new transients were reported to us, if one was particularly promising, just based on its location and its brightness, we would go and use X-ray telescopes to follow it up and check whether there was any X-ray emission. That didn't happen in the 4 years that we were doing that. So they're coming up with new strategies at the moment, but that is a valid technique for finding them because it worked at least one time. So we know that it should work in theory in future. Any questions at this point?
No.
Okay. Okay, so what can we learn from the velocities of gamma-burst supernovae? This outline is not linear, so don't worry, there isn't like 80% of the thing left. Okay, so this is the picture you got to keep in mind, okay? We can be viewing it from within the jet, we can be viewing it outside the jet, okay?
Okay.
We've got a supernova. We've also got a gamma ray burst coming out along the polar axis like we talked about earlier. Here's my pitch to you, basically, right? This gamma ray burst jet is inside all of this gas and it has to get out. You would assume that as it gets out, it gives some energy to the gas that it's pushing aside, right? So I would imagine that that should increase the velocity of that gas.
The gas, yeah.
Yeah. So if I'm observing here, so looking into the gamma ray burst jet, or slightly out of it, so that I'm looking maybe here, I should see a higher velocity from that supernova than if I was looking, equatorially out here, where I'm just seeing kind of a normal supernova, right? There is some historical precedent for this. So back in 2016, someone studied a bunch of gamma ray burst supernovae and just regular supernovae, and they found that the gamma ray burst ones, seem to be higher up here on this velocity time plot. Okay, so there's some evidence that this is a real effect. It's not exactly clear how robust it is, though, because these error bars overlap quite a bit, right? So it's not a really clear-cut signal. So what I wanted to do was I wanted to find out in events where we know there's a gamma ray burst jet, right? So those ones where we actually saw a gamma ray burst, we know there's a jet there. Do those events have higher velocity than other 1CBLs that didn't have a gamma ray burst? So that was the goal of my thesis.
Sorry, Gabriel, when you say you're looking at that, you're not looking at that, Joe, right? This is coming from your spectrograph.
Yes, exactly. Or even, so you would look with optical telescopes first, but then you would do spectroscopy later. Yeah.
Redshift or that, yeah.
Yeah, so you'd have to correct for redshift as well, obviously, because your spectrum will be shifted because of the expansion of the universe, and you are trying to look for a much smaller signal. So, the first time I did it, I didn't take off the redshift, and I was very confused as to how the velocity was as high as it was, but
if some of the material is ejected at 0.1 speed of light, you've got a blue shift coming towards you.
Exactly, yeah. So you're expecting a blue shift here of up to 30. There was one that was reported at 70,000 kilometers per second, which is 20% of the speed of light, which is insane. It's kind of weird that was the one that was in theory off axis, so we weren't within the jet, because that kind of implies that there's a wider range of angles where you'd see a high velocity. So it's interesting. There's not. It's very hard to distinguish, is this a viewing angle effect, or is it just, do some of them just not have gamma ray bursts? Okay, so I collected up a really big sample. So I found 850 spectra from various different sources. Had to go through them all manually, which obviously took a month or two. Was very, very boring, but get interesting results. So I started with 234 inverted commas 1CBLs, because sometimes when we're doing our classification, we can get it wrong. So the first spectrum isn't always reliable. You can often need to look at a few different spectra to get a gauge of what type of supernova it is. So I narrowed it down, and eventually I ended up with 61 what I'm going to call 1CBLs. So these are the ones that don't have a gamma ray burst. And 13 GRB supernovae, so ones that had a GRB and were 1CBL supernova as well. Okay, so velocity is basically the motion of this gas. That's what we're measuring. Anytime we talk about velocity, it's just, is this gas moving towards us? Is it moving away from us? And yeah, we use the Doppler shift to calculate that. Okay, Now it's time for graphs with loads of dots on. So this plot has a lot of information on it. It's got all of the iron line velocities, and then on the right hand side it's all of the silicon line velocities. So I measured these two, and to me it's not clear that there's a separation between the blue points, which are gamma ray burst supernovae, and the orange points, which are normal supernovae. There isn't like a clear line that I can draw through this plot that, you know, you can say if you're above this velocity, you definitely had a jet, or if you're below, you didn't have a jet. So it's somewhat inconclusive, to be honest. We can't, you know, use these velocities to say you definitely had a gamma ray burst that we just didn't see, or you didn't have a gamma ray burst. Which is a bit disappointing after you spend ages on supernovae spectra, but it's useful in terms of we need to find another way to look at this, basically, and that way is probably going to have to be to go and look in radio and in X-rays and see signs of the gamma ray burst that can be seen at wider angles. And in that case, you might be able to label some more of these as gamma ray burst supernovae. You might detect evidence of the jet, and then that may reveal that there is actually some separation there that we can't see at the moment. So I then looked at basically how are these velocities evolving. So lots of people have looked at kind of, you know, is this velocity higher than this velocity on this particular day? But they hadn't looked at like, how does this velocity compare to this next one that was measured a week later or 2 weeks later? You know, what's the shape of that curve? No one had looked at that. So I decided to find out what it looked like. So I found that it can be described in two different ways. So we have these things called power laws. Okay, power laws are everywhere in astronomy, but you can essentially think of it as a straight line on a plot that's drawn with a log axis on both axes. Okay, so if you make both of the axes of your plot logarithmically scaled, then you get these straight lines, and these straight lines represent power law equations. Yeah, so you got these power law ones where basically it just declines and it keeps declining at the same rate for, you know, a few weeks. We've also got these broken power laws. So these broken power laws are more interesting than the power laws. So the power laws are kind of what you would expect from an expanding ball of gas. There's kind of some simple physics that you can do to say, okay, the photosphere kind of recedes inwards as the temperature drops, and, you know, energy can escape without running into the atoms that are in the way. But broken power laws are much harder to explain. So if this is real, and there needs to be some more work done to make sure that these are real effects, then it's really exciting because it could indicate new physics. So the new physics in this case would be identifying two different parts of the ejecta that are moving at different speeds, basically, right? That is further evidence for a jet if it's real. So a jet is believed to introduce some asymmetry into the explosion. So you can kind of imagine kind of an elongated explosion rather than a spherical explosion. The power laws might be evidence for that, but we don't know yet. Okay, and that's just some histograms. Yeah, so I also looked at kind of comparing velocity and the steepness of the decay. So the steepness of the decline in velocity and the actual velocity value at 15 days. And there's maybe some more separation for iron here. You could maybe say that this group up here is, you know, ones that might have had a jet. There's a few more blue points up here than orange points. But again, it's hard to say. The one thing I can say for certain is that on average, you can say that 1CDLs with gamma ray bursts are expanding more rapidly, which is what people had said previously, and I don't think that's true based on this larger sample size. Okay. Interestingly, I found that it's almost always the silicon velocity that declines faster than the iron velocity. I can't explain why this is. It's just an observation that I made whilst doing this research, and it needs kind of a lot more interpretation to know why this is happening. but it could be an indication that they're coming, like I said, from, maybe an aspherical ejecta, so something that isn't spherical. There's maybe portions that are moving faster than other areas, but not clear yet. Okay, so we're at the end now. So I wanted to find out whether all 1CVLs have a GRB jet, and I did this by measuring the velocities of a bunch of different ones that had GRBs and ones that didn't have GRBs. Couldn't find any clear separation between the groups. Now, it's interesting in some ways because it means that we can't use velocities to distinguish between these groups, and that's really interesting. Simulations would have suggested that we could have been able to do that, but apparently we can't. The velocities of both of the groups seem to show power law or broken power law evolution. We can explain the power law evolution very easily, but broken power laws could mean something about the shape of the ejecta, which is also cool. So I think that's the last slide I have. No, I have a couple more. Yeah, that's all right. Okay, questions?